Welcome back to mass transfer operations 2 course. We were discussing on humidification and air conditioning. Till now we have discussed on humidification and cooling tower design using this individual gas phase mass transfer coefficient as well as overall mass transfer coefficient. And now we will be discussing on the dehumidification and air conditioning. So, before entering into this subject, we should know something about the dehumidification process and air conditioning. So, the process in which the moisture or water vapor or the humidity is removed from the air, keeping its dry bulb temperature constant, is called the dehumidification operation. In actual practice, the pure dehumidification process is not possible, as the dehumidification operation is accompanied by either cooling or heating of this air. So, this process is represented by a straight vertical line on the psychrometric chart, starting from the initial value of the relative humidity, extending downwards and ending at the final value of the relative humidity. The process in which air is cooled sensibly and at the same time the moisture is removed from it is called as cooling and dehumidification process. Cooling and dehumidification process are obtained when the air at the given dry bulb and dew point temperature is cooled below the dew point temperature. The process in which the air is heated and at the same time moisture is removed from it is called this heating and dehumidification process. So, this process is obtained by passing the air over certain chemicals such as alumina or say molecular sieves. So, now we will be solving one dehumidification problem, and from there we will be learning that how this moist warm air is cooled, or we can say this one dehumidification operation is done in the which is used in the air conditioning system. The problem is this moist warm air is to be cooled and dehumidified in to a wet bulb temperature of 30 degree Celsius using water of 25 degree Celsius in a dehumidification column. The air enters the tower with a dry bulb temperature of 85 degree Celsius and wet bulb temperature of 45 degree Celsius at 4719 kg per meter square hour rate. That is, we can say this one rate of moist air. The overall gas phase mass transfer coefficient is estimated to be 2150 kg per meter cube hour. The flow rate of actual water is 1.4 times the minimum. Now, we have to calculate this minimum water flow rate, outlet water temperature, which will be coming out from the cooling tower, and moisture removed from air during this process and height of this tower. So, we need to design one dehumidification column. The process is almost similar. There are some changes we will be discussing step by step. This one, first of all, we need to find out that what will be this relative humidity and enthalpy values for the given problem. Say Tg1 is 85 degree Celsius, that is given in the problem. This Tg1 is 85 degree Celsius and Tw1 that is 45 degree Celsius. So, now we will start from this here 45 degree Celsius and we will move, because this is Tw1. So, from here we will move in the vertical direction till the 100% saturation, and then we need to follow the adiabatic saturation curve like in this line, through this line, and we will move from 85 degree, that is we can say this Tg1 to the vertical direction, and we will be touching one point, and from here actually we will be moving towards the y2 axis, and from here we will be getting this y1 prime, that is nothing but it is 0.047 kg per kg dry air. And if we move in the vertical direction in the wet bulb temperature, we know that say this is wet bulb temperature, and if it reaches the adiabatic saturation, enthalpy of the saturation air, from there actually we will be getting this, we can say, enthalpy of this air which is entering here, that is H1 prime. That is H1 prime is nothing but say 210 here. It is 210. So, this is 210 kilojoule per kg dry air. So, this is, so now we have got this, what is the relative humidity of this gas, this air entering from the bottom of the cooling tower, and H1 prime, that is enthalpy of this moist air at, that is 210 kilojoule per this kg dry air. So, that is we have got this one 047, take this. And also this H1 prime we already discussed this one, H1 prime also we can get from this relative humidity also, like H1 prime, that we know that is nothing but is equal to 1.005 plus 1.88 into this one y1 prime, that is nothing but 0.047 into this Tg minus T0, that is Tg means say for this case it is 85 minus reference temperature is 0 plus 2500 into 0.047. So, that also will be coming as 210 kilojoule per kg dry air. So, now we have the all the conditions of the dry air which is entering from the bottom of the dehumidification tower. Okay. But we note this one, this wet bulb temperature of the outlet air, that is actually 30 degrees Celsius. Now, we can say this one wet bulb temperature of outlet air, that is given in the problem, that wet bulb outlet air will be equal to say 30 degrees Celsius. That is actually our requirement. Okay. So, it is nothing but we can say this one, this is nothing but it is adiabatic saturation temperature. So, in that case, as it is adiabatic saturation temperature, so whatever the enthalpy value, that is actually fixed. So, if this enthalpy value, enthalpy will become now this one irrespective of this, we can say the temperature. Enthalpy is, so that is at this one, at this condition, that is say we can say this one enthalpy is now fixed, and that is irrespective of temperature. Whatever the dry bulb temperature it will attain, but this enthalpy will remain constant, because that we have this one given the problem as this wet bulb temperature of the outlet air will be 30 degrees Celsius. Okay. Now, say we need to find again that what will be this y2 prime, that will say again we will be going to that this psychrometric chart. Say now you see this one, this now say it is 30 degrees Celsius. At 30 degrees Celsius, say we can say this one will be following this line. So, whatever the say saturated enthalpy that will be getting, that will be H2 prime, just simply just we can say this, we can go up to this one, and from here we will be moving to this one, that is H2 prime. So, this H2 prime will be say 98 kilojoule per kg dry air, and correspondingly at that 30 degrees Celsius, whenever it will be attaining this wet bulb temperature of 30 degrees Celsius, the relative humidity that is also fixed, like this, say it will be like this, that is we can say this one y2 prime, that is say it is nearby 0.027, that is kg per kg dry air. Okay. So, now we have this H1 prime, H2 prime, then Y1 prime, Y2 prime, Tg1, Tw1. So, we have most of the values. Now, we are trying to make this, we can say this one, we can say dehumidification column like this. We will be trying to get this dehumidification column like this. So, this is this station 1, this is station 2, and this hot air actually is entering from this bottom, and cold water is this one falling from the top. Okay. So, now we can say this one, now we need to get whatever the GS value we will be getting, we are getting this GS is equal to say whatever the G1 gas flow rate is there plus 1 plus this Y1 prime. So, this flow rate is given that is given as 4719 divided by 1 plus 0.047. So, it is coming out to be as 4507.04 say kg per meter square hour. So, that is kg per meter square hour. So, GS is equal to 4507.04, and then Tg1 that is given as 85 degree Celsius, and Y1 prime is obtained as 0.047, that is we can see this kg per kg dry air that is present, and H1 prime the enthalpy value is obtained as 210 this kilojoule per kg, and whatever the cold air that will be coming out from this dehumidification chamber. So, we can say this dehumidification tower. So, their GS that is fixed, so GS actually will remain constant, that is nothing but 4507.04, and Y2 prime that is as this we can say the wet bulb temperature is fixed at 30 degree Celsius, the Y2 prime will become like 0.027, and H2 prime that is we can say this one that is becoming 98 kilojoule per kg. And here this whatever the cold water actually is entering, that say liquid flow rate we need to find out whatever liquid flow rate actually we have, but we know that TL2 that is already given that is 25 degree Celsius, and whatever the hot water will be coming out. So, this liquid flow rate till now we do not know, because we need to find the what is the minimum water flow rate we will be finding out, and then we will be multiplying with 1.4 times, then we will be getting whatever the liquid flow rate is, and we do not know this TL1 also, that is also now we do not know this liquid flow rate, we do not know this we do not know this liquid flow rate, as well as we do not know whatever the outlet temperature of this water, that is we can see this coming out from the bottom of this dehumidification column. Okay. Now, we have this one say bottom condition we have already, or we can say this one that is the lower terminal of the operating line. So, now we will be drawing this the equilibrium line, whatever we draw this one for this case also it will be like this same, we will be drawing this equilibrium line. I think we know how to draw the equilibrium line, and then we have this bottom terminal of this we can say dehumidification column. Now, it is you see this above this we can say equilibrium line, that is TL2 is equal to this 25 degree Celsius, and say we can say this Q is this we can say this lower terminal of the operating line. So, lower terminal operating line, that is Q, which has the dimension of like this temperature and enthalpy value T1 and enthalpy, that is as US, this is 25 degree Celsius and 98. So, now we have located this lower terminal of the operating line, or that is we can say this one point Q. Okay. Then the enthalpy of the feed air at the bottom point, actually, that is we can say this one at P, we do not know where the actual P is, we can say this one, but you see this one that enthalpy value actually we know, because you see this one, whatever the moist cold air which will be leaving from this dehumidification chamber, that temperature is fixed as wet bulb temperature or adiabatic saturation temperature as 30 degree Celsius. So, enthalpy of this we can say this one bottom point, or we can say this one bottom this one upper terminal of the operating line, we can say this one, that enthalpy of upper terminal of operating line is 210 kilojoule per kg. So, that what we will be doing this, now we will be doing one parallel line of this temperature line. So, it will be like this, but where this point P, actually we can say this one we do not know. So, the point P of this we can say this one, or we can say this one upper terminal, we do not know where this actual P will be, but whenever we will be say doing this, we can say minimum water flow rate. So, now we will be doing the calculation of the minimum water flow rate. So, we will be doing this one. So, for that, so we can say we need to find the pinch point, whatever we did for the humidification column. Say from the lower terminal we have drawn the tangent to the equilibrium line. Here also we will be drawing we can say this one straight line to this, we can say this one pinch point, where it will be touching this 210 kilojoule per kg. So, from here actually we will be drawing one straight line up to this, we can say this one 210 kilojoule per, this one what is called, that is the enthalpy of the exit air. So, that is actually where it will be touching, that is called pinch point. So, this is actually nothing but pinch point. So, this point is called this pinch point. So, there enthalpy value definitely it will be 210 kilojoule per kg dry air. Okay. Now, say we can say whatever the water flow rate, say minimum water flow rate actually will be getting. We have this one, if we do this overall, we can say this one enthalpy balance, then it will be like this, say Gs into say H1 prime minus H2 prime is equal to say LS minimum into TL minimum minus TL2 into TL2 into CWL. So, here all the values are known to us except this LS minimum. So, we will be putting here like this, that is 4507.04 into that is 210 minus 98 is equal to LS minimum into TL minimum, that is we can say this on whatever the water that will be coming out from this dehumidification column, that is we are getting as say here it is say 45 degree Celsius. So, that is 45 degree Celsius minus TL2, that is already given in the problem like this 25 degree Celsius, and that is CWL is equal to 4.187. So, from here we will be getting LS minimum is equal to, that is 4507.04 into 210 minus 98 divided by 45 minus 25 into 4.187, that is coming out to be as 6028.05, so kg per meter square hour. So, this is the minimum water flow rate required to get that wet bulb temperature of 30 degrees Celsius, but this the outlet temperature of the water will be shoot up from 25 to 45 degrees Celsius, but actual flow rate actually is given as that actual flow rate will be. So, this is the first this one question which is asked in this problem, that what is the minimum water flow rate, that is nothing but 6028.05 kg per hour meter square. Now, we say we need to get this actual water flow rate. Like this, again we are drawing this equilibrium line, then from here say we are coming to this point P, but you see this one actual water flow rate is equal to 1.4 times of this LS minimum. Okay. So, it is coming out as 1.4 into 6028.05 is nothing but 8439.27 kg per meter square hour. Okay. So, that is, say for this case we can say what will be this, say now we have this one, this actual water flow rate, or we can say this one LS, that is we can say this one LS. So, now LS is equal to 8439.27 kg per meter square hour. So, say using the same equation like this overall enthalpy balance equation across the dehumidification tower. So, we will be getting what is the minimum temperature of the water to be maintained if this actual water flow rate is 1.4 times of the minimum water flow rate. So, we will be again applying this same equation like this, Gs into H1 prime minus H2 prime is equal to LS into TL1 minus TL2 into CWL. So, here Gs is equal to say 4507.04 into, that is 210 minus 98 is equal to, now we have this LS is equal to 8439.27 into, so we need to get this whatever the TL1, that is what will be the water temperature that is leaving the dehumidification tower. Then TL1 is equal to TL2 is equal to 25 into 4.187. So, here, so we will be getting this TL1 is equal to, say from this equation after manipulation we will be getting TL1 is equal to say 39.29 degrees Celsius. So, this is the second question asked, that is we can say this one B. So, this liquid, whatever the liquid water will be exiting from the cooling tower, it will attain 39.29 degrees Celsius. Now, you see this one is like this. So, 13.29 degrees Celsius, this is the line. So, now we have this, we know that this temperature, the enthalpy of the, we can say this one air which will be leaving the dehumidification tower is 210 kilojoule per kg dry air, and the liquid temperature is 39.29. Now, we have this upper terminal of this one, and now we need to draw a straight line from this lower terminal of the operating line to the upper terminal of the operating line. Now, we say we will be giving this, the third question that is asked like this moisture removed this from air that is nothing but we can say this how much amount of water actually is condensed during this process per hour. That is we can say this one G s into say y 1 prime minus y 2 prime. So, that is we can say this one 4507.04 into 0.047 minus 0.027. So, that is coming out as 90.14 say kg per meter square hour. So, this is the we can say this one how much moisture removed from the air during this process, that is we can say this one the answer of this problem C. Now, we need to find out the what will be the height of this dehumidification tower. So, now what we will be doing, we will be getting this NTOG and HTOG, and then we will be multiplying this NTOG and HTOG, and we will be getting like. Now, say we need to get the what is the area under this curve. Say it is worthy to mention here that for the case of this humidification tower, the operating line was just below the equilibrium line, but in case of this dehumidification tower, the operating line will always lie above this equilibrium line. Now, you see we need to do this one what is called we need to get the area under the curve. For that we will start from say this one we know that the temperature of this liquid water this is 25 degree Celsius, and the we can say this one temperature of this hot water that is 39.29 degrees Celsius. So, in between this we need to get what will be the enthalpy value and what will be the enthalpy we can say equilibrium enthalpy value, or in all the cases you see this equilibrium enthalpy values will be much more lower than the actual enthalpy value in the say air. So, we need to find out this one. Now, the equation will be like this for this area under the curve. So, we will be taking say suppose we will be taking one TL, for that we will be getting one enthalpy and we will be getting one equilibrium enthalpy like this one, and this now this for getting this area we will be getting H star 1 by H star minus H star prime, because here you see this all the times this H star will be lower than the this one actual enthalpy value. So, we will start from 25 degree Celsius. For that this enthalpy value from this one what is called graph will be getting 98, that is already we have derived, and whenever we will be moving towards this equilibrium line that value is actually 75. So, now this 1 by 98 minus 75 that is coming out to be 0.043 like this. For this again we will be taking any temperature say increment we can do this one. So, whatever we are this following this 27.7, for that this enthalpy value is 117 and this equilibrium enthalpy value is 85, and then 1 by H prime minus H star prime we are getting as 0.031. For 30 degree Celsius we have this enthalpy value is 136.9, whereas equilibrium enthalpy value is 98, and this 1 by H prime minus H star prime that is coming out H 0.026, and then for 32.5 degree Celsius the enthalpy value is 155.4 and equilibrium enthalpy value is 110, and the 1 by H star minus H star prime is 0.022. For 35 degree Celsius the enthalpy value is 176, H star prime is equal to 130, and 1 by H prime minus H star prime is this is also 0.022. For 37.5 degree Celsius, that this enthalpy value is 195.3, whereas this equilibrium enthalpy value is 145, and 1 by H star minus H star prime is 0.02, and for 39.29 degrees Celsius, this we know this enthalpy value we have already calculated, that is at 210 kilojoule per kg dry air, and equilibrium enthalpy value is 156, and this 1 by H star minus H prime minus H star is 0.019. So, now we are getting this one, the entire space actually we are getting this area under the curve, this total portion actually we will be getting. So, we will be getting now NTOG and HTOG like this one. Now, we see HTOG will be getting from the equation, that is well known equation, this HTOG, that will be nothing but GS by capital KY prime A bar, that is given as this GS value. GS is the 4507.04 divided by, that is given as KY prime A is given as 2150. So, it is coming out as say 2.096 meter, and NTOG. So, NTOG will be getting, this is as say H2 prime to H1 prime into DH prime by H prime minus H star prime. So, in case of the humidification column, that denominator was H star prime minus H prime, because you see this one, in case of this humidification column, the operating line was below this one, that is why the difference of equilibrium enthalpy and the actual enthalpy was positive, but in this case as the operating line is above this equilibrium line. So, the actual enthalpy minus equilibrium enthalpy gives the positive value. So, this is we are getting as for the entire range, say 210 minus 98 into 0.026. So, that is we are getting as 2.912. So, now we have this HTOG and NTOG, from there we will be getting this height of this dehumidification column, that is we can say this one total height of dehumidification column is equal to HTOG into NTOG, that is coming out as we can say 2.096 into 2.912 meter. So, that is nothing but 6.104 meter. We can say this one height of the dehumidification column. So, that is the end of this. So, the area under the curve is obtained as this one, and so will be the now the total system is like this. The gas flow rate is 4507.04 kg per meter square hour. This inlet air temperature is 85 degree Celsius with humidity is 0.047 kg per kg dry air, that is the absolute humidity, and enthalpy value is 210 kilojoule per kg dry air, which is this. So, that is why we can say this one more hot air is entering, and whatever the cold water is entering, that is at 25 degree Celsius with actual flow rate is 8439.27 kg per meter square hour. So, but that is the we can 1.4 times of the minimum water flow rate, and the whatever the cold water actually air that is leaving from this dehumidification column, that is we can say this wet bulb temperature, actually we can say this one Tg2, we can say this one coming out as say that is T wet bulb, actually we can say this one wet bulb temperature, that is as 30 degree Celsius. Okay. And the flow rate will remain same, because this is this one per kg dry air, that says 4507.04 kg per meter square hour, and with the humidity much lower than this whatever humidity was there in the inlet this one air, that is 0.027 kg per kg dry air, and enthalpy value is 98 kilojoule per kg. And whatever the liquid water, this one we can say this hot water will be leaving the dehumidification tower, that temperature is 39.29 degree Celsius, and liquid flow rate, that is we can say this on 8439.27 kg per meter square hour. And if this liquid this one what is called this outlet liquid water temperature is, if it is 45 degree Celsius, then the liquid flow rate will be 1.4 times less than 8439.27 kg per meter square hour. So, in the next class we will be discussing on drying operation. So, thank you.